We'll start on the, whatever we ended up in the first part. This is second part. I think we discussed the last thing in the first part about the uh, oxidizing agent and reducing agent. So now let's look at the another example here. Here we have iron react with oxygen to produce iron 3 oxide. This is iron 3 oxide. Okay, so let's look at the oxidation states for each of iron and oxygen. Iron by itself is 0 because it's just neutral element, and oxygen is a molecule by itself, neutral, is 0. Oxygen within any chemical compound, most of the time we say it -2. And iron here, because it's 3 here, iron has to be 3 plus. And you can confirm this. 3 positive multiplied by 2, 6 positive from iron. -2 multiplied by 3, -6 by oxygen. +6, -6 makes 0. So it's a neutral compound. So now let's look at this. What's happened to iron? Iron is being oxidized from 0 to 3. It's an increase, correct? So it's oxidized. What's happened to oxygen? Oxygen from 0 to -2 is reduced, correct? So ask yourself again, as we said, what does iron do on oxygen? Iron is forcing oxygen to be reduced from 0 to -2, correct? So iron is reducing agent and itself will be oxidized, correct? Good. What does oxygen do on iron? Iron is forcing oxygen to be oxidized from 0 to +3. So oxygen is an oxidizing agent and itself will be what? Reduced. Okay, let's look at another example here. Dichromate 2- and +2 hydroxide ion give us 2 chromate plus H2O. If you look at the chromium ion here is +6 oxidation number. Oxygen is -2. Oxygen is -2 here in the hydroxide ion. Hydrogen in the hydroxide ion is +1. Chromium in chromate is +6. Oxygen is -2 in the chromate ion. Hydrogen in H2O is +1. And oxygen is in H2O is -2. So for me, I don't see any change. It's the same thing. There's no oxidation, no reduction. Therefore, this type of chemical equation is not a redox at all. So this is not a redox. So no redox. This is a normal chemical reaction, no redox reaction. Let's go and look at some examples. This is a very unique example. This is ammonium nitride, gives us nitrogen and H2O. You can think ammonium nitrate as ammonium by itself and the nitride ion by itself. Ammonium ion by itself, nitride ion by itself. And it looks like the ammonia, the nitrogen here, the nitrogen from the ammonium, is the hydrogen is +1 because covalent. We said when hydrogen is combining itself with the covalent bond is always +1. -1 if it's combining itself with the metals. So nitrogen therefore will be -3. In the nitride here, oxygen is -2, correct? And nitrogen, if you look at this, nitrogen will be, because you have to add all this together, nitrogen is +3, correct? So, and if you look at this one here, nitrogen in this is 0, hydrogen is +1, oxygen in H2O -2. Now, what's happening here, that's ammonium nitride. It's happened to it, the 2 nitrogen, one of them is oxidized and one of them being reduced. The ammonium here goes, the nitrogen and ammonium from -3 to 0. This is oxidation. This is what? This is oxidation. The other nitrogen in the NO2 minus, from +3 to 0, that is a reduction. So we have the nitrogen is in different oxidation states. So think about ammonium ion. The nitrogen in ammonium ion will be oxidized, while the nitrogen in the nitrite ion will be reduced. Let's look at another example. I have phosphorus by itself, an element, P4, 0, and I have chlorine as an element by itself. Of course, you know, chlorine cannot be as elemental element by itself, but always combining as is a molecule, and the same thing is an element. So chlorine will give us the phosphorus pentachloride. The chlorine is always -1 within compounds. The phosphorus will be +5, -1 +5, -5, and phosphorus +5. Now, ask yourself, what does phosphorus do on chlorine? Well, phosphorus is forcing chlorine from 0 to -1. That's a reduction, correct? So phosphorus is a reducing agent. Itself will be what? Oxidized. What does chlorine do on phosphorus? Chlorine is forcing phosphorus from 0 to +5, being oxidized. So chlorine is an oxidizing agent, and itself will be reduced. Let's take this one here. Okay, let's take this one here, and let's look. We have chromium 3+ plus H2O plus chlorate ion, give us dichromate plus chlorine dioxide plus H2 plus. So let's look at this. Here we have chromium is 3+, but chromium here is +6, correct? This is an oxidation, very obvious an oxidation because it's an increase, correct? Hydrogen is +1, oxygen -2, and hydrogen +1 and oxygen -2. That's not change. So we know the oxygen and hydrogen is not changing. How about chlorine? Chlorine is +5 here and +4. So chlorine is being reduced. So chlorine is being reduced in chlorate from +5 to +4 in chlorine dioxide, and the chromium ion is being oxidized from +3 to +6 in the dichromate, correct? So again, which one is oxidizing, which one is reducing? Ask yourself the question. What does chromium do on chlorine? Chromium is forcing chlorine to be reduced. So chromium is a reducing agent, and itself will be what? Oxidized. What does chlorine do on chromium? Chlorine is forcing chromium to be oxidized from +3 to +6. So chlorine is oxidizing agent, itself will be what? Reduced. Let's go further. Balancing redox reaction in acidic medium. This is a little bit more work, more demanding, and it's not really difficult to do. It's very straightforward, but a little bit more steps needed. So in this type of the balancing redox reactions in acidic medium or in basic medium as well, we have to watch the two half reactions. The oxidation reaction by itself, the half reaction, and another half is the reduction half reaction. So let's look at this this unbalanced reaction, net chemical equation here. The bromide ion with the permanganate ion will give us bromine plus manganese. So let's divide it in two, correct? This is manganese half reaction, and this is the bromine half reaction. So this is from -1 to 0. This is an oxidation, correct? This is an oxidation here, and this is +7, as you will see, +7 to 2. This is for sure is reduction, correct? Let's see here the next step. Yes, that's what we did. So we have to balance just the bromine. We have 2 bromine here, so I have to multiply this by 2. 2 bromine, it's 1 bromine, correct? Now it's balanced. We did not balance the charges yet. We will come to that. We'll come to that. But at least 2 bromine to 1 bromine. This is an oxidation. Now I have to balance the negative charge. I have a negative charge here. How I balance the negative charge? I have to introduce electrons, correct? So one bromine will give us 1 electron. 2 bromines here will give us how many? 2 electrons. That's oxidation. Oxidation is giving away electrons. So this half reaction is producing electron. This is an oxidation. Okay? And it goes from -1 to 0. That's an oxidation reaction. Let's do the permanganate. Let's look at the permanganate here. We'll balance the manganese inside the permanganate. So we have 1 negative charge permanganate, give us Mn2 plus. Well, it looks like we have to deal with oxygen here. Here there is no oxygen. So we have to add what? We have to add water here to compensate for oxygen. How many H2O we have to add? We have 4 oxygen. So we have to add 4 H2O here, correct? To balance the 4 oxygen there. Now, looks like atom-wise they are balanced. Atom-wise they are balanced. However, when we introduce ourselves H2O, we are having now the hydrogen here, the protons. There are no protons this side, so we have to bring 4 multiplied by 2, 8. So we have to add the next step, the 8 protons here with the in front of the with the permanganate to compensate for the 8 hydrogen this side. Correct? It is balanced? No, by all means. Why? Because here we have 2 positive charges and here we have 1 negative charge and 8 positive charges. So it's the net here is 7 charges and here is 2 charges. 2 charges and the net here is -1 plus 8 positive, that's plus 7. So something is not correct. So how we can balance it? Well, we come to we look at the idea that the permanganate is 7 plus 7 manganese here, and here's 2. So plus 7, so 7 here, correct? Plus 7 here, and here's 2. So how many the difference? 5. So we have to add this reduction, correct? The reduction, it has to be taking in electrons. So we have to add 5, what? 5 electrons. 5 electrons. So 5 electrons with H plus 1 manganate. This is now balanced. So it will be 2 positive in the left, because 5 plus 1, 6 negative, and 8 positive is 2, and here we have 2 positive. So this is now balanced. And if you go back and look at the bromine here is nicely balanced. We have 2 negative charges and 2 bromine ion, 2 negative. So everything is balanced now. Let's look at the next step. The next step, so this half reaction is consuming electrons, gaining electrons. So this is a reduction, correct? Because plus 7 to 2. Now, we have them both, reaction balanced with, again, if we have oxygen here, we have oxygen here, we have to produce H2O. H2O is added. Whenever we added H2O, we have to add the protons in the other side. So this is very nice balance. Now the problem is not balance here, is our electrons. So this electrons here, 5 electrons, and here is 2 electrons. So how can I balance it? Well, I'll swap. I multiply this here, equation here, by 5, correct? Why? Because this 5 here by 5, and this equation by 2. So I swap. This is 2, we'll use it here, and this is 5, use it here, correct? Use it here. So now I have the bromine equation here. 5 multiplied by 2, 10 bromine, give us 5 bromine ion and this bromine gas plus 10 electrons. And here 2, 10 electrons, 2 multiplied by 8, 16, 2 multiplied by manganese, 2 manganese, 2 multiplied by permanganate, by manganese 2 positive cation and 8 H2O. Now I have, this is a reduction, this is an oxidation. Now I have to add them up, correct? The electrons, 10 electrons in the left will cancel out in the reactant side with 10 electrons in the product side will cancel out, correct? So then after canceling the electrons, I end up with a very nice balanced chemical equation looking like this. Now the unique about this, look at this. This is the balancing of this chemical equation done in acidic medium. We use 16H plus for the balancing this chemical equation. So this is an acidic. So this is an acidic. So the question is, what is the oxidizing agent? I think we answered this. The oxidizing agent is the permanganate forcing the bromine to be oxidized from -1 to 0. Itself will be reduced. Which one is reducing agent? Is the bromide ion forcing the permanganate to be reduced from +7 the manganese to +2, correct? Itself will be oxidized. So this is, we answered this. And I say that's what I said here. Here it is. We use the protons to just to put emphasis that the reaction goes by acidic medium. Can I do this reaction in the basic medium? Yes. I have to add enough OH, enough hydroxide ion to compensate for this. So I will add 16 OH minus to eat up, to consume all the protons here. That will be the next step. So here it is. I have to add 16 OH in both sides, correct? And by doing this, so 16 OH, if you look at this up, if you add 16 OH minus, 16 H plus, you make what? 60 molecules of H2O. H plus plus OH minus, that's H2O. So you make 16 H2O, and that's the 16 here. So this is the 16 H2O here. And by doing this, you have the 16 OH coming here. So this is the 16 H2O here, because you added both sides. And here your 8 H2O to begin with. Now here is 16, here 8. So the subtracts from the bigger to the smaller. 16 minus 8, 8 will come in this side. So 8 is here. And here will be OH. So this is, reaction is done, carried out in basic medium. Let's show you what's produced is hydroxide, and this is in the hydroxide because you added enough hydroxide ion to the reaction. So let's look another example here. We'll have the oxidation of methanol by dichromate to produce methanol or form aldehyde, and chromium by this process will be reduced to chromium cation 3 plus. So as you know, this is primary alcohol. Primary alcohol is oxidized to give you aldehyde, and secondary alcohol, if you recall from survey of chemistry 2, will give you ketone. This one we have an aldehyde, methanol, or formaldehyde, common name, being oxidized with the oxidizing agent is dichromate. So let's look at which one being oxidized, which element being oxidized, which element being reduced. So hydrogen looks like, and oxygen is not changing. Hydrogen always +1 in covalent bond. Oxygen always -2. So oxygen is -2. Oxygen is -2 here. It's not changing. Correct? Hydrogen is +1, not changing. What's changing is carbon and chromium elements. So carbon here is -2, correct? Look at this, -2, and here is 0. So from -2 to 0, that's oxidation, correct? Increase. 0 is greater than -2. So this is an oxidation, correct? And from chromium +6 to 3, this is a reduction. So we have here a redox, half redox reaction, and here we have an oxidation, correct? Reaction. We have two halves. oxidation, and we have here reduction. Let's look let's balancing them together. Now if you look like this, CH3OH, CH2O, the oxygen is 1, 2 hydrogen, and here 4 hydrogen. So you might have to add what? 2 hydrogen plus, okay? Remember this one in aqueous solution. You added 2 hydrogen plus 2 to balance the hydrogen. That's what we did here. So we are balancing what? The hydrogen here. In the other one, we have 7 oxygen. We have to add H2O to balance the 7 H2O. We added 7 H2O to balance the oxygen here, 7 oxygen in dichromate, correct? By doing this, I have produced hydrogen here, protons. So 7 multiplied by 2, 14. So I have to add the other side, 14. So now we are dealing with two equations, correct? That's a reduction, and this is the oxidation. So now we'll go through what? To balancing the charges, correct? We have to balance the charges. Now if you look at this, this came from -2 to 0. So it has to give 2 electrons. So the oxidation half reaction has to give 2 electrons. Here it came +6, correct? Here this chromium is +6. 2 + 3, it has to gain 3 electron. However, we have 2 chromium here, 2 chromium, each chromium 3. So we have to add how many here? 6. That's dichromate, means 2 chromium. It will have 2, so 2 chromium here. So it has to be 6 electrons. Now, if you look like this, these 6 electrons I have to cancel. So the easiest way is to multiply this equation here by 3 to get the 6 electrons and add them both together. So multiply this by 3, 3 methanol plus 6 electrons plus 14H plus dichromate will give you the methanol or formaldehyde, 3 molecules, 6H plus 6 electrons plus 2 chrome plus 7. So what I did here, I just multiplied the oxidation, half oxidation chemical equation by 3 to make 6 electrons. So I can then at the end, the 6 electron, the product side with the 6 electron from the reactant side cancels out. And what I can cancel out, I can cancel out the 6 protons in the product with the 14 in the reactant. I'll end up with 8 here, and this will be then the balanced chemical equation. This is the balanced chemical equation. And again, in acidic medium. Why acidic medium? Look at this one here. H protons means in acidic balancing. Balancing was carried out in acidic medium. If I want to make this one here in basic medium, I have to add enough, correct? OH minus. So let me go back. So I have this one here, and it has H plus. So I have to add what? OH minus. 8 proton ion with 8 hydroxide ion will make 8 H2O here. The other side, I have the other products is I have 8 negative. So I have here 8 because I added to both sides 8, correct? When I added both 8 side, the 8 with the 8 will make what? Those here together will make this H2O. 8 H2O, chromium, methanol or formaldehyde, plus 7 H2O, correct? 7 H2O, this is from the 7 H2O from the reaction itself. It came there. We're balancing the oxygen, 7 dichromate, 7 oxygen. So now we have 7 H2O here. So subtract this. 8 is bigger than 7, so move the 7 to the other side. Is we have 1 H2O, and the reaction is carried out in the basic medium. Okay. Now let's look at the chemical reaction stoichiometry. If you look at the potassium chlorate here, decomposition reaction will give us potassium chloride and 2 moles of potassium chloride and 3 moles of oxygen. If you have 2 moles of potassium chloride, this is balanced equation. And we can make a ratio that's 2 moles of the chlorate, potassium chlorate, will give us 2 moles of potassium chloride, or 2 moles of chlorate will give us 3 moles of oxygen, correct? So we can use this ratio for the calculation. For example, just here an example, and you can see, you can go through all this example together, and let's make maybe 1 and 2, and then the other ones, I think, straightforward. Well, we can do all of them. Let's see here. It says how many moles of oxygen will be formed from 1.6 moles of potassium chlorate. Potassium chlorate is the reactant, and it's given to us. You start always whatever given to you. Then you put the ratio, potassium chlorate at the bottom. Why? We always, the key success for this type of reaction is unit cancellation. Then you look what's asked. Asked is moles of oxygen, so the moles of oxygen has to be up. We have 3 moles to 2 moles of oxygen to 2 moles of chlorate. So the chlorate moles cancels out. You have 1.65 multiplied by 3 divided by 2 give you this moles of oxygen. The same thing if you're asked if you have how many moles of potassium chlorate are needed to make 3.4 moles of the potassium chloride. Well, take this one at the beginning here. Whatever is given to you is you start with. And then you put it at the bottom to cancel the unit. So mole potassium chloride with the mole potassium chloride. Then go to mole ratio. I have 2 moles of potassium chloride to 2 moles of chlorate. So this one cancels out, and then 3.50 multiplied by 2, multiplied by 2 moles, divide by 2, and give us 3.5 potassium chlorate. How many moles of potassium chloride will be formed from 2.73 moles? This is given to you. You started with, it's not clear here, but it's 2.73 of the chlorate that's given here, has to be coming here, correct? And 2 moles of the chloride that's asked, and to 2 mole of the chlorate, 2 to 2 moles, so the mole chlorate cancel out the mole chlorate here, and 2.73 multiplied by 2 divided by 2, that will give us 2.7. The answer is 2.73, correct, of the moles of KCl. Okay, so now here is how many moles of O2 are produced if for this reaction here. If you look this reaction here, well, it looks like the same thing is given to you. 1.26 mole of H2O, mole of H2O at the bottom to cancel it out, and 2 mole of H2O will stand to 1 mole of oxygen. So mole H2O cancels out. 1.26 multiplied by 1 divided by 2 will give you 0.6. This is 0.6, 0.630 mole oxygen, correct? So now go further. If enough H2O is reacted to produce 3.4 moles of hydrogen, then how many moles of oxygen must be made? Well, it looks like you start with whatever is given to you. This is given to you, correct? 3.4 mole of H2O. Now this mole ratio, to get rid of the mole of hydrogen, you go back and look. I have 2 mole of hydrogen to 2 mole of H2O, 2 mole of hydrogen to 2 mole of H2O. So I have, or the oxygen, if I want the oxygen, I have 1 mole of oxygen and 2 mole hydrogen, and 1 mole oxygen to 2 mole of H2O. So let's look here. I have 1 mole of oxygen to 2 mole hydrogen, and the mole hydrogen cancels out. I have 3.40 multiplied by 1 divided by 2. I get moles of oxygen. Now let's look at our old example here. How many grams of oxygen will be formed from 3.7 grams of potassium chlorate? Well, you start whatever is given to you. That's always the key. Okay, that's whatever is asking me. I have to get rid of the grams through dividing by the molar mass. This is the molar mass, gram per mole, correct? So I get the grams out of my way. So this gram with the gram cancels out. The mole, I have to get mole of this one here because I'm looking for oxygen. So I'm looking for the action. I put mole oxygen asked for me. That's what I'm looking for in the top. And the given to me in the bottom, so I can get rid of the moles with the moles out. I have 2 moles of potassium chlorate to 3 moles, so 2 to 3. 2 what? To 3. And then I have to multiply it by the molar mass of oxygen to get number of grams. So 4 steps. First, whatever is given to you of grams of the reactant, divide by the molar mass of the reactant here, then the mole ratio from the chemical equation, balanced chemical equation, and then multiply it by the molar mass of the product to get the correct answer. Now, if you look at this, how many grams of potassium chlorate are needed to make 30 grams of potassium chloride? Here is the products is given to you. Well, you start with it. As we said, divided by its molar mass, just the molar mass of potassium chloride. To get rid of, unit cancellation is the key, the grams of potassium chloride. Then the third step is to get the mole ratio. So the percolate rate is asked, which is 2 mole here. Look at this 2 here, 2. And the potassium chloride is 2. So 2 mole of potassium chlorate to 2 mole of potassium chloride. And this is the molar mass multiplied by the molar mass, gram per mole. So the mole cancels out the mole of chlorate, the mole chloride, potassium chloride, the mole chloride cancels out. And you do all the calculation, you end up 49.3 gram of potassium chlorate. Further, how many grams of potassium chloride will be formed from 2.73 grams of potassium chloride? Again, you started with this. Here it is, correct? With the grams. You divide it by its molar mass. Grams with the grams cancel out. Here it is. Grams with the grams cancel out. Gram per mole, that's the divide by the molar mass. Then you have to get rid of the potassium chlorate moles. Go to ratio 2 moles. Let's look up again. We have 2 moles per chlorate to 2 moles of the chloride, 2 to 2 moles, correct? So then you multiply by the molar mass of potassium chloride, gram per mole. So the mole with the mole cancels out. The only unit left is grams of potassium chloride, which is 1.66 gram. Okay, let's consider another one. We have here this ammonia synthesis as a combination reaction, synthesis reaction, and this is an exothermic reaction. It says how many molecules of ammonia produce if one has used 0.750 moles of nitrogen. Well, if I have something, the keyword molecules, it means what? It means I have to use what? I have to use Avogadro's number. Immediately, without hesitation, anytime I ask about molecules, there's Avogadro's number 6.022 10 power 23 have to be used. That's what we get the number of particles, which can be molecules, atoms, or formula units, ions, correct? So let's look at this example here. We have 0.750 moles of nitrogen is used, and we need to number of molecules of ammonia, of the product. So we start whatever is given to us, moles of nitrogen. I go to the equation, I have 2 moles, here it is, 2 moles of the product ammonia to 1 mole of the reactant nitrogen. So the mole of the nitrogen with the mole of nitrogen cancels out. I have to get rid number of moles of ammonia, so I have to multiply it by Avogadro's number, which is 6.022 10 power 23 molecules ammonia per 1 mole of nitrogen. So mole nitrogen here cancel with, mole ammonia, not nitrogen, cancels out with mole ammonia here, correct? And then you do calculation, 0.750 multiplied by 2 multiplied by Avogadro's number gives you the amount of molecules of ammonia. B, how many ammonia produced if you have 1.8 moles hydrogen? The same steps, the only difference here you have to watch. Hydrogen, you start with it, so 1.80 moles. But now the ratio is different. You have 3 moles of hydrogen when you have 2 moles of ammonia. That's, you have to look at the ratio only. And then you multiply it by the mole, by the Avogadro's number to to get number of moles of molecules of ammonia, to get number of molecules of ammonia. So now let's look at if we have to calculate number of grams, correct? We have to calculate number of grams. We have zinc sulfate. We react with strontium chloride to get strontium sulfate with zinc chloride. It says calculate the mass of strontium chloride is consumed when 55.0 gram of zinc chloride is produced. And then the other one, this time we are calculating the zinc chloride, one of their products. The other one we have to calculate the strontium, another product, is consumed when 85 gram of zinc sulfate. So we have to look at strontium, the mass strontium sulfate being consumed when 80 points is produced. So, well, we have to look at the whole thing. As I said, you start in A here, 55. We start with this zinc chloride, and we are looking at strontium chloride. So we are looking at the reactant side. We need to produce how much. So this has to be started with, that's A. This is zinc chloride, correct? That's started with, it's given to you, divided by its molar mass. You divide it by its molar mass. Then you go to mole ratio, 1 mole ratio to 1 mole ratio, 1 to 1. And then you have to multiply it by the strontium chloride molar mass, which is this one here. So again, the amount of the grams of the product, zinc chloride, divided by the molar mass of the same product, zinc chloride, then the mole ratio is 1 to 1. Then you multiply it by the molar mass of the reactant strontium chloride to get the answer here, 3 sig figs, correct? So, and this is here the molar masses of both, the molar masses of both. In B is the same thing. We started with 88.5 gram of zinc sulfate, correct? That's the reactant. And you divide it by the molar mass. Here it is the molar masses we are looking for. You divide it by the molar mass of zinc sulfate, correct, which is 161.5. So you started with this zinc sulfate amount in grams. You divide it by the zinc sulfate molar mass, 1 to 1 mole ratio. Then you multiply it by the strontium sulfate molar mass, which is here given to you here, to get the number of grams of strontium sulfate. Straightforward. So let's look at the yields of reactions. Here we have to calculate the limiting reactants and the theoretical yield. And as I said, we have this carbon monoxide. We react with hydrogen to give us the methanol. This type of reaction called synthesis or called combination. Again, it's a redox reaction. As you can see, it's a redox reaction. And if we have 12 grams of hydrogen and 74.5 grams of carbon monoxide are used to determine the limiting reactant. So I don't know which is limiting, which is excess. Therefore, I will base my calculation of my yield, theoretical yield, on the number of moles of the products based on each one of them separately. And then compare number of moles of each to see, correct? To see how is the least number of moles will give me the limiting reactant, which I base my theoretical yield final calculation on. So I base my final calculation for the theoretical yield on the limiting reactants of one of the limiting reactants moles, the least one, the least number of moles. So let's look at the number of moles. Here it is of the methanol based on CO2. Now we are looking at the CO2 first, carbon monoxide. This is carbon monoxide, 74.4 gram is used, correct? I divided by the molar mass of carbon monoxide, which is 28 gram per mole. And then I look at the mole ratio. I have 1 mole of this, of methanol, to 1 mole of CO. So 1 mole of the product to 1 mole of CO, I get 2.66 moles of methanol based on 74.5 grams of carbon monoxide used. Now let's look at if I use 12.0 grams of hydrogen. So 12.0 gram of hydrogen divided by the molar mass by hydrogen, which is 2 gram per mole. And I have 1 mole of the product methanol will stand up to what? To 2 moles. So the 2 here, don't forget the 2 mole of hydrogen, and it came out to be 3.00 mole of methanol. Now we have here, look at this, here it is 2.60, and here we have 3.0. Which one is the least? The least is 2.66. So the number of moles of my product methanol based on carbon monoxide will yield the least number of moles. So carbon monoxide is our limiting reactant. Correct? This is very important. And hydrogen in this case is our excess reactant. We are not interested in the excess reactant. We are interested in this limiting reactant. Now, how much is the least number of moles? 2.66. Well, then I have to multiply it by the molar mass of methanol, my product, to get number of grams. Okay, so here it is, 2.66 mole. Okay, and multiply this one here by the molar mass of methanol to get 85.1 gram methanol. So now there is another question here, very nice. It has 4 really question by themselves, which is very interesting to look at that 4 question by themselves. So we have a propane. Propane will be combusted. It's a combustion reaction, correct? This again is one of the redox type reactions. The combustion reaction yield always CO2 plus 4H2O, and we are not worried about the calculation with the heat, but it's always the heat will be we'll just make a here it is. The heat will be just a triangle here. So let me just put the triangle. That's the heat plus heat. So now if I use the propane, 0.550 gram propane, correct, with 0.55 gram of oxygen, we have to calculate the amount of CO2 produced based on the limiting reactant. So we have 2 reactants, propane or oxygen, propane and oxygen. Which one is the limiting reactant? We don't know based on whatever this amount here, correct? 0.550 grams. And then we have to calculate the theoretical yield based on this limiting reactant. And then we have to calculate the overall yield based on the actual yield is 0.55 grams. Then we have to calculate the percent yield, percent error yield. So there are four different calculations, and this is a very nice example. One example has all those 4 topics at the same time. So let's look at the first one, the limiting reactant. Well, it turns out to be, we'll start with, I have to look at the chemical equation. I have 3 CO2, 3 moles to 5 moles for oxygen, and 1 mole of propane. This is very important, correct? So we have, I know propane and oxygen, they have the same amount, 0.550 gram each, but the number of moles in the balance equation is different. 5 moles for oxygen will yield 3 moles of CO2. 1 mole of propane will give us 3 moles of CO2. So let's go here. So I have 0.55 grams. First of all, I have to look at the propane, C3H8. So 0.550 grams of propane divided by the molar mass of the propane, correct? And then I look at the molar mass of the mole ratio from the balance equation. 3 moles of the product CO2 will stand to 1 mole of the propane. So I get the value of 0.0375 moles of CO2. That's the amount of the product produced if I use 0.550 gram of propane. And those are just the molar mass here. Those are the molar mass I use. Now let's do the same calculation based on the oxygen. 0.550 gram oxygen divided by the molar mass of the oxygen, multiplied by mole ratio is 3 to what? To 5. So we have to look at this. 3 to what? To 5. This is 5. This is 3. In the top was what? It was 3 to 1. So 3 here. Look at this. And to 1 here. But here we have 3 to 5. Now, with calculation of this, I get what? 0.0103. Here I get 0.037. So which one is the least? The least is 0.100, correct? 0.1. This is the least here. This is the least. So therefore, oxygen is the limiting reactant. Oxygen is the limiting reactant. Now, the theoretical yield based on the limiting reactant, I get this one here, correct? That's the least, multiplied by the molar mass of CO2, the products, 44. I get 0.572 grams CO2. The overall yield is defined as actual yield divided by the theoretical yield multiplied by 100%. So the actual yield is given to me is 0.550 grams. I divide this one here by the theoretical yield, calculated yield, 0.572 multiplied by 100, I get 96.2% yield. That's the overall yield, which is very good, excellent yield. So now the percentage error of yield, that's the formula. Theoretical yield minus actual yield divided by theoretical yield multiplied by 100, and everything is in absolute value. You take the absolute value. Theoretical is 0.72 minus 0.550 grams divided by 0.570, and the whole thing absolute value multiplied by 100 get you 3.85%, which is very, very small percentage. So it looks like the reaction went very smooth and yielded a large, excellent yield. Now we'll go for the quantitative chemical analysis. Well, it turns out the quantitative chemical analysis is a branch of chemistry that's dealing with the exact amount or the percentage or the exact amount of the components during the chemical reaction. And those analysis can be is used as, we can use gravimetric analysis. There's a couple types, we will discuss just 3 of them. Gravimetric analysis, titrometric analysis, which is titration, and then elemental analysis, which is using combustion reaction. We combust the sample. So let's look at first of titration or titrometric analysis. In this titration analysis, we have a burette. We actually put the base inside this burette, and Erlenmeyer flask, which has, so the burette with the base, and the Erlenmeyer flask will do the acid. So here it is. That's the base here, and this is the acid. And inside the acid, we put indicator. Suppose I have here sodium hydroxide, and I put here vinegar. So I put phenolphthalein 3 drops, correct? And I titrate until the color of the solution turns from colorless, phenolphthalein acidic medium is colorless, and it switched to light pink color. And therefore I stop the reaction. The reaction has ended, and therefore I can calculate the exact concentration of the acid. So I worked with the very exact concentration of the base to determine. So the base is, I have the known concentration, but I have to determine the exact amount of the acid, the exact concentration of the acid. So titration is used not only for acid base, it's used even for other reaction, for other compounds as well. So this is how we can see. Now, if you look at the whole thing, we can use indicator, which give us the color, which is not really that much of accurate. But if I use pH meter, then the data and the results will be much more accurate. And there is difference between the pH meter and the indicator in 2 things. They will give me The pH meter give me the equivalent point. So here it is. This is the pH meter. And the indicator usage will give me the endpoint. What is the difference between the endpoint, correct, and the equivalent point? Well, it turns out to be the equivalent point is by which is the number of moles of the acid equal the number of moles of the base. So the reaction is done. But the pH meter can give us a very good data on this. But we use the cheapest method, which is the indicator method, which give us the signaling the change of the what they call the change of the color, of the acidic, from the acidic medium to the basic medium. So the change. So the difference, if you look, see the difference here between them is a very, very tiny difference. It's really negligible. It's not that much. So again, equivalent point, number of moles of acid equal number of moles of base, and then we have the endpoint, which is signaling the change in the color of the solution when we use an indicator, signaling the changing of the pH of the solution. So the indicator works, it gives us different color in different medium. So this is titration and this is one of the example how we do titration. We put KOH in the burette. This is, we put sulfuric acid inside the Almayer flask. We add a couple drops of the phenolphthalein and titrate, and those are the byproducts. And then when the indicator signals change from colorless to light pink, we stop the reaction and read how much is used of sodium hydroxide, amount or volume, and then record the volume sodium hydroxide and do the calculations. Now let's do here. If we have read after the end of the reaction 35 mils, that's the end point. The indicator had stopped, changing the color at 35.0, correct? That's the end point. And we have the exact molarity of KOH we have used, 0.150 molar, and we have used of sulfuric acid 35 mils as well. What is the molarity of our sulfuric acid? Well, it turns out just straightforward. So I use the potassium hydroxide, correct? This is, I have to convert this one here into liters. So this is the liter of KOH. This is the molarity this is the molarity here. This is, it is, yeah, this is the volume in liters. This is the molarity of the KOH. So therefore the moles, the liter with the liter cancels out. I have moles. I go for the ratio. I have 1 mole of sulfuric acid here to 2 moles. So 2 here, and here is 1. Understood, not written is 1. So I have 1 mole sulfuric acid to 2 moles of KOH. Then I have to divide the whole thing by the volume of the sulfuric acid, which is here in liters. So with the whole calculations here, 0.035 multiplied by 0.150 divided by 2, and then the whole thing divided by 0.035 liter, I get 0.075 mole per liter as 1 unit, or 0.075 capital M, or 0.075 molar. So there are three types of expressing the molarity: mole per liter, capital M, or molar. Let's go for gravimetry. Gravimetry, here is an example, another method for quantitative analysis. Gravimetry, for example, used to determine the toxic lead ions inside water we drink. So how we can do that? Well, we have this, here's the sample, correct? And with this sample, we dissolve the sample. This is the water solution here. Step 1, we dissolve it, correct? This is the sample here, we dissolve it, and then we add, after dissolving the sample here, we add to it, which precipitate the lead as sulfate. We can add to it sodium sulfate, for example. So we precipitate then we add the sulfate ion as sodium sulfate, and then we precipitate at the bottom here our lead sulfate. And the amount of lead in lead sulfate will determine the percentage of lead inside our drink water. So, and after what? Let's go up here again. Here is the solid lead sulfate. Then we have to take this solid here and do the vacuum filtration, which is here. This is a vacuum filtration setup. This is a Buchner funnel. It has some small tiny holes, supports lane. And this is just a vacuum for the water pump. And we put the pre-weighed filter paper, pre-weighed, and then we decant the beaker here with the lead solid solution, and we decant it through, and the liquid will come through. This is liquid, and the solid, then lead sulfate will be trapped inside. So inside the filter paper is our lead sulfate. Then after that, we take it and put it in the oven. The pre-weighed, we know the weight of the mass of the filter paper, pre-weighed filter paper, and then we take it in the oven overnight, and then try to weigh it and then determine the amount of lead sulfate. And then from the lead sulfate amount, we can determine the amount of lead inside our sample of the drink water. Here's an example. Here's just a similar example here. If I have 0.95 grams of solid mixture containing potassium sulfate dissolved in water and treated with an excess of barium nitrate, so resulting in precipitation of 0.850 gram barium sulfate. This is after the vacuum filtration, after the precipitation reaction. So we get we added the sulfate to the barium, so we have precipitated barium sulfate there, and we are interested. The solid came out as a precipitate, and it said the barium nitrate added. This is in excess. The limiting reactant is potassium sulfate. Now we have to know how much potassium sulfate in the containing mixture 0.9550 based on 0.850 of barium sulfate. Well, let's start. We started with whatever is given to us, 0.50 gram sulfate, correct, divided by the molar mass of the barium sulfate. And then you go to look, I have the molar ratio. I have 1 mole of potassium sulfate in the top, that's I'm looking for, given to me 1 mole of barium sulfate, and then the whole thing multiplied by the molar mass of potassium sulfate. That's what the desired one, that's what I want. I want to get the number of grams. So it looks like I'm ending up with 0.635 gram of potassium sulfate. Now you ask yourself, this is just the molar mass of barium sulfate and potassium sulfate. So how much is now the percentage? The total is 0.95. So you take the whatever you have got here, 0.635 gram potassium sulfate, divided by the total mixture amount in grams, multiply by 100, that will give you 66.5% of potassium sulfate present inside the mixture. Let's look at the last one here. The last one for the elemental analysis, they called combustion analysis. The combustion analysis is oxygen here is the excess reactant, correct? And the compound is said to be combusted will be your limiting reactant. We heat, This is a tube here. We have a catalyst. This is a catalyst here. This is our catalyst. So just to help the reaction to go faster. So we are combusting the material with the excess of oxygen. And then whatever is coming out of the combustion will be what? Will be H2O and CO2. That's coming after if any combustion. So then we have H2O absorb H2O, and the difference in the weight to begin with, and then the end of the reaction, that will give us the amount of H2O inside the sample, which it turned out we can turn up the hydrogen. How much is it? So here the same thing, CO2 absorbs CO2, and then the difference in from the beginning and the end of the reaction will give me the amount of CO2, and from there we can determine what? Determine the amount of carbon dioxide, and then from there we can determine the moles of carbon, and here from H2O we can determine the hydrogen. So with the help of those two we can determine the empirical formula and then the formula of the compound. Correct? Let's go further here. The combustion reaction, if you look here, is carried out under excess of oxygen, as I said, passed through closed tube, which is heated. The carbon hydrogen present in the sample are converted into carbon dioxide. Here it is, and H2O here. The excess O2 helps to push through the products through the tube. So inside the tube we have a catalyst, copper 2 oxide catalyst. This is similar like nickel palladium in the catalytic converter in the cars, and catalyzes the conversion of the combustion of any compound, correct, to CO2 and H2O. Now H2O corrected in the absorber of the absorber for H2O, it is magnesium perchlorate is used to absorb H2O, correct. The change of the masses will give us the amount of H2O, and CO2 is collected in a separate absorber filled with sodium hydroxide. The difference in change in the masses will give us the amount of CO2. If we have nitrogen and oxygen, we can get them by difference from the mass combusted sample and the sum of the masses of carbon in the carbon dioxide and hydrogen in water. So let's look at one of the example here. This is elemental analysis of an organic compound using combustion reaction reveals that we have 2.6406 grams CO2 and 0.5400 gram H2O. The molecular formula given to us is determined to be 78.11 gram per mole. That's determined by other means. GC mass spec or any other means can be determined the molar mass. But we have the molar mass and we have both CO2 and H2O. How in the world we know what's really the structure of the compound? That's what we are at. We are looking for the structure of the compound. Well, we are not worrying. We will do this one here. This is the equation here. We'll put ourselves the equation. This is the combusted material compound, the hydrocarbon compound, CXYH plus excess of oxygen will give us X of CO2 and Y over 2 H2O, correct? Y over 2 H2O. Then you have to convert the gram of CO2 into carbon and the grams of the H2O into hydrogen. So let's do that. So 2.640 grams CO2 divided by the molar mass of CO2, and I have 1 mole of carbon, correct, to 1 mole of CO2. So I get what? I get 0.0600 mole of carbon. So carbon here is determined. The hydrogen is 0.450 gram H2O, 1 over 18, that's the molar mass of H2O. And I have 2 moles. We have to watch for this, and that's what we have here. Y over 2 because hydrogen is 2. So we have 2 moles here of hydrogen in 1 mole of H2O. So I get the same thing here. What? This is hydrogen. So if I look at this is, look at this, 0.06, and this is 0.6. This is 1. Divide them both, and 1. So the empirical formula for this is C1H1. So this is the empirical formula for this compound. Why? Because it came up the number of moles 0.06 for carbon and 0.6 for hydrogen, 1 to 1. Now let's look at this. The empirical formula, if you recall from the previous part of the chapter, the empirical formula is the molar mass of the whole molecule divided by 13 gram per mole. From where is the 13 gram per mole? Well, this is C1H1, correct? C here is 12, and hydrogen is 1. So you add them up, that makes you what? 13. So the empirical formula unit is the molar mass of the whole molecule, actual molecule, divided by the molar mass of the empirical formula. The empirical formula is C1H1. The molar mass of the empirical formula is 13 gram per mole. The given molar mass of the whole structure is what? Is 78 point. And it turns to be what? 6 units. So 6 units multiplied by 6 multiplied by C1H1, and the molecular structure, the molecular formula, the molecular structure of the compound is C6H6, which is benzene. This is the structure of benzene. Thank you very much for listening.